Well, you may not have thought of a connection between Newton and Kepler. There is a fairly strong mathematical link. Newton determined that for a force such as gravity that depends inversely on the square of the distance, that's a mouthful, the only stable shape for orbits is an ellipse. Newton would have been able to tell himself he was on the right track with his gravitational force law by noting that Kepler had determined that the planetary orbits are ellipses. We won't go through all the details of the mathematics leading from Newton's law of gravitation to Kepler's third law, but for the simpler case of circular orbits, we'll look at a couple of relations that come out of that, which will help us understand some key points about how orbiting objects behave. Here's Kepler's third law, Kepler's version of Kepler's third law. The p squared equals ca cubed, and hopefully by now you know that p is the orbital period and a is the semi-major axis. With Kepler's law as this is written, we usually use the orbital period in years and the semi-major axis in astronomical units. Some key things about this. This law was discovered. Kepler was analyzing the huge amounts of data gathered by Tycho and discovered that this happened to be the case. As far as Kepler knew, this law only applied to the 6 planets orbiting the Sun. At the time, there were only 6 planets known orbiting the Sun. And also at the time, these were the only orbital situations Kepler had decent data for. As far as he knew, it was only true for those. Newton was able to expand somewhat on this. There were some comets that appeared in the early 1680s, and he studied their motion, and then he wrote to other people and got as much data as he could from them, fine-tuning that. And he discovered that these comets obeyed Kepler's laws as well, and that helped him finalize his universal law of gravitation. By combining the law of gravitation with Newton's second law of motion and a couple of other mathematical relations, you can come up with a version of Kepler's third law that's based on the gravitational force, and it bears a lot of similarity to the Kepler version. For one thing, it still has the square of the orbital period and the cube of the semi-major axis, but now we can see that the constant depends on the strength of the gravitational force. For one thing, it's got that capital G down there on the bottom, the universal gravitational constant, and it's got the mass of the Sun in there. The reason that all the planets and everything else orbiting the Sun have the same constant in them is because they're all orbiting the Sun, and that's what governs the behavior as they're orbiting. This version can be applied to any orbital situation, and it's no longer limited to planets orbiting the Sun. It applies to satellites orbiting planets, both natural moons and man-made objects, planets orbiting other stars, stars orbiting the centers of their galaxies, with some modifications that you have to do in that case, and any situation where gravity causes an object to orbit. There is one correction we need to add here. The top equation there is an approximation that works just fine for objects orbiting the Sun, and whenever you have a fairly small object orbiting something that's much more massive. The more correct expression includes both the mass of the object doing the orbiting and the mass of the object being orbited. Now, in the case of the solar system, the most massive planet, Jupiter, is 1/1000th of the mass of the Sun, and so you'll only be off by 1 part in 1,000 if you ignore the mass of Jupiter. So you'll be 99.9% correct if you ignore Jupiter's mass. Ignoring the masses of the other planets and their orbital motion is a much smaller error, and so we can safely ignore those. You can do a little bit of math and solve for the mass of the orbited object, or the sum of the masses of the two objects, if you want the more precise version. This yields the mass of any orbited object. In the lab astronomy class, we use a computer simulation to determine the orbital radii and periods of the Galilean moons. That's Io, Europa, Ganymede, and Callisto. And from that, we can figure out the mass of Jupiter. And we usually do pretty well on that lab. The big problem is people using scientific notation on their calculators correctly. Even planets that don't have moons, we can use this on. In written homeworks I've used before, I've included a question. We know the masses of all of the planets that have moons because we can study the motions of their moons. We know the masses of Venus and Jupiter, even though they don't have moons. How could we possibly know that? And then I give a hint. We have close-up pictures of those planets. How did we get close-up pictures? We put spacecraft in orbit around them. And spacecraft obey the same orbital laws that natural moons do. And so you can use their orbits to figure out the masses of whatever they're orbiting around. We've also discovered thousands of exoplanets, and these are planets that are orbiting other stars, since the first were discovered in the 1990s, and by studying the orbits of these exoplanets, we can accurately determine the masses of the stars that they're orbiting. We can also determine the masses of stars when the star is in a binary star system, and a surprisingly large fraction of stars are. In fact, more than half of the naked eye stars in the night sky are part of binary systems. And by studying those orbits carefully in the binary star system, you can determine the masses of each of the two stars. It's a little more work than if it was something not so massive like a planet, but you can do that. So now we're going to limit ourselves to circular orbits here, and I'd like to develop a relation for the speed of an orbiting object. The speed of an object in an orbit is v equals d over t. This may look a little familiar, although in an algebra class you'd typically use r is equal to d over t. In physics, instead of talking about rate, we often talk about velocities, and so we use v. If we're talking about speed, we just talk about how fast it's going and not which direction it's going in. If we want the velocity, we also have to include the direction. But that's why we have a v here. So v is just distance divided by time. Now, if something is traveling in a circular orbit, the distance it travels in one orbit is 2 pi times the radius. I'm using a for the radius here. So 2 pi a, that's the formula for the circumference of a circle, divided by p, the orbital period. We could play around with a bunch of algebra and get an expression for the speed in terms of basic properties. You have to use the law of gravitation, a relation for the acceleration of something that's traveling at constant speed in a circle, and something else that escapes me at the moment. Maybe that's all we need, actually. Maybe Kepler's third law. When we do that, we get v is equal to the square root of gm over a. And so this is a fairly simple expression, the square root of the gravitational constant times the mass of the star or the object being orbited divided by the orbital radius. What can we get out of this thing? Even with those parts under a square root, we can see some important tendencies. One is, the larger m is, the more speed is required of the orbiting object at a given distance. We'll see this where we compare some different planets in the solar system and the speeds of their moons compared to Earth's moon. The orbiting objects don't have any choice about their orbital speeds. They have to either be going at the correct speed, or if they're going too slow, they'll fall in closer to the planet, possibly even hitting the planet. If they're going too fast, they'll move outward to a farther orbit. Maybe if they're going way too fast, they'll actually lose the planet and leave it behind. And for a given object being orbited, the larger the orbital radius, or the larger the semi-major axis, the slower the speed of the orbiting object. And let's just look at the planets in the solar system as an example. Here we've got the 8 major planets and Pluto in the solar system, and we have the semi-major axes of all the planets shown here, and those are all measured in astronomical units. For astronomical units, the semi-major axis of the Earth's orbit is the standard that we use to define what an astronomical unit is. The orbital speeds here would be an average orbital speed, because the speed varies throughout an elliptical orbit, but not by a huge amount. And so these orbital speeds are pretty close to the average. But look at the speed of the Earth. It's moving at 29.8 kilometers per second, which is about 18.5 miles per second, or almost 67,000 miles per hour. But look at Mercury. It's going about 60% faster than the Earth, and it has to. Where Mercury is, the gravitational force from the sun is so much stronger that if it wasn't going that fast, it would move in even closer to the sun, possibly falling into the sun. Then look at Jupiter. It's going less than half as fast as the Earth is. If you ever wonder why Jupiter takes so long to orbit the sun, it takes about 11.9 years for Jupiter to orbit the sun, you have to say there are 2 reasons. One, its semi-major axis is 5.2 times as large as Earth's orbit. That means it has to travel, because the circumference is proportional to the semi-major axis, it has to travel about 5.2 times as far in its orbit. But that's only half the reason. The rest of the reason is that Jupiter is going less than half as fast as the Earth. And the combination of traveling 5.2 times as far and traveling less than half as fast is what makes Jupiter take 11.9 years to orbit the sun. For a more extreme example, look at Pluto. Good old minor planet Pluto. If you look up its orbital period, it's about 249 years. That's a long time. Part of the reason is that Pluto has to travel about 40 times as far as the Earth does, or 39.5 times as far, but that's only part of it. The other part is that Pluto is only going about 1/6 as fast as the Earth is. You have to combine those things to know why something takes so long to get around the sun. Okay, this shows how the orbital speeds of the major planets and Pluto drop off in speed as you move farther out in the solar system. Pluto is only going 1/10 as fast as Mercury is. This is Pluto way out here, and then Mercury is in here. You can see how this drops off steeply at first and then kind of flattens out, but it keeps going downhill. Here's a few Earth orbiting satellites here. Quite a range here. The orbital speed of the International Space Station, 7.66 kilometers per second. The moon out there, both the Hubble Space Telescope, which is HST here, and the International Space Station are going more than 7 times as fast as the moon happens to be in its orbit. And finally, take a look at this graph here. I have a curve up here for the orbital speeds that would be required in the Jupiter system. And I have vertical lines for 4 of the moons of Jupiter, the 4 Galilean moons. This is Io here. It's not low, it's capital I, lowercase o. And then Europa, Ganymede, Callisto. If you want to know how to remember those, I eat green cheese. And then if you can remember the names, that helps. Then I've also got the Earth's moon marked on here. Now, Io and the Earth's moon have orbits that are very close in their semi-major axes measurements, and they're nearly round, so they're just about circular orbits. Io's actually a little farther out. So if it was in orbiting the Earth, if Io was at that distance, it would be going about as fast as the moon, which is only a little over 1 kilometer per second. But in the Jupiter system, it has to be going almost 18 times faster than the moon. Europa still going way faster than the moon, all the way out to Callisto here. It's almost 5 times as far from Jupiter as the moon is from Earth. But it has to move faster than a satellite in low Earth orbit. In fact, Callisto is moving faster in its orbit than the International Space Station and the Hubble Space Telescope have to move around Earth. That's some information about orbital speeds and how they depend on the mass of the object they're orbiting and the distance from the object they're orbiting.